Okay, we are at chapter 19, magnetism. Uh, we've all have uh, or find magnets interesting. At least I do, and I have it ever since a little kid. Um, but we'll start with the PowerPoint, and if you look, this is a tokamak. I forget what tokamak stands for. It's a Russian word, and I know the toe is a toroidal, and you can see that it is a toroid shape. This figure that they're showing you is a toroid shape. Now, if you haven't noticed, there's a man on the inside, off to the left side, kind of in the circle there. And what these toroids do is they um, using a magnetic field, they contain a plasma uh, inside. And this particular one, this is the uh, tokamak fusion test vacuum vessel at the Princeton Plasma Physics Laboratory. So seeing the man inside there, that gives you a sense of the scope of this. I know University of Texas had one. I saw the door to the tokamak. I never saw the actual tokamak. That's where I did my master's degree at UT Austin. Uh, I don't think it was anywhere near this side. So this magnetic field contains the plasma that they inject into, or that they produce by this. Okay, here's a typical horseshoe magnet. If you were present for the fields and equipotentials laboratory, you saw we shook some iron filings onto a piece of paper so you could map the magnetic field coming from the north to the south. It's when we talk about charges, there's a lot of similarities between charges and magnets. The fact that like charges repel and unlike charges attract. Like magnetic poles repel and opposite magnetic poles attract. So a north will attract a south, and a north will repel a north, and a south will repel a south. And there's lots of similarities. Even the fields that are produced by a magnet look a lot like a little dipole with a positive and negative. But where the similarity deviates is if I were to break this red and gray magnet, I wouldn't get just an isolated north pole and an isolated south pole. If I were to break this magnet right at the division, I'd get a new north and south, and then another south and north. You always have them in pairs. They are trying to find magnetic monopoles, in other words, just the north or just the south. Hasn't been done yet. Some people believe that it'll never be done. Some people say, well, don't ever say what science can't do, because you'll be wrong. Yeah, I tend to be on the side to think that they won't find it. So typically you always find magnets in pairs. Whenever you have a north pole, you will have a south pole. If you keep breaking this piece over and over, you'll still get a north pole and you'll still get a south pole. Okay. Then there's different magnetic materials. This is a picture of a magnetite. Magnetite. There's soft magnetic material such as iron that easily magnetizes, but it also easily loses its magnetism. Others are nickel iron alloys, and ferrites. Hard magnetic materials are used in permanent magnets. These magnets provide magnetic fields without the use of electricity. Probably the strongest ones you come across are the neodymium, the very shiny silver-looking neodymium magnets, and these are used in speakers, motors. They're used in several different applications. Um, so Alnico is an alloy of iron, cobalt, and nickel. Um, then there's the rare earths, samarium and neodymium. Is neodymium magnets are prolific. You see them all over the place, or the production of them. You see them all over the place. Um, but anyway, so here's a image of a magnet, and if you were to take a small compass and move it around this magnet, you would see that the north pole of the compass is going to always be attracted towards the south. Those near the this by the north, they're being repelled by the north, so they're pointing away from it. And as you move them over to the right side, they're attracted to the south, and so you can see that they make magnetic field lines that look very similar to the electric field lines that you would get in a pair of positive negative charges. So you, here you see the magnet stripped of the little imaginary compass, and it just shows you the magnetic field lines. Okay, and you should have done this um, in your equipotential lab, spreading the iron filings over a magnet. You have a single magnet, and you can see the north and the south and the pattern they give. Here's a north and a south, but two different magnets and the pattern that they give. And then here's two norths, and you can see that line between them where they oppose each other. Okay, and that's actually the last on uh, that slide. Let's see if there's anything else I need to say about that. Okay, we'll stop that.